In this video, I want to talk about a math trick that Schroeder uses in equation 1.17. So to begin with, let's look at equation 1.16. 1.16 is a relationship between 1/2 mvx squared, the kinetic energy in the x direction only, to kT for the gas. And what Schroeder then wants to do is he wants to be able to relate the total kinetic energy, 1/2 mv squared, where v takes into account the velocity in all directions, to the temperature of the gas as well. So the goal is to take and expand this vx squared to be v squared. And in doing this, he uses a trick that's and describes it as the average of a sum is the sum of the averages. So what Schroeder ends up showing is that the average velocity squared is equal to the sum of the average velocity in each direction squared. So the equation begins with, there's a 1/2 out front, but it's just a constant, so we can not worry about it. The first thing that I think is important to show is that mv squared, the average of that, is actually equal to m times the average of v squared. And the idea here is this average we can write as the sum, where I runs over all of the possible particles. So I runs from 1 to n, where there are n possible particles. We add up the mass times the velocity of the ith particle, right? Particle 1 plus particle 2, etc. Each particle, we take the mass of that particle times v squared. Since every particle has the same mass in our ideal gas, we're assuming that there's just one type of particle in the gas, then we can pull the mass outside of this sum, right? Just like if I have, for example, a times x plus a times y, I can write that as a times x plus y, right? If I have the same factor multiplied by each of the terms in a sum, I can just pull it out. So I can pull that outside of the sum, and then this sum divided by the number of particles is just the average velocity squared. So that's one of the tricks that gets pulled out. The other one is this average of the sum is equal to the sum of the average. So here is our velocity squared average. And what we're going to do is we're just going to expand it out by writing all of the sums explicitly. So here we have we're summing up vi squared over n particles, right? And then we can write vi, the ith particle, we can write its velocity squared as just vx squared plus vy squared plus vz squared. This is just Pythagorean theorem, how we can write the magnitude of a velocity squared in terms of the square of its components. And again, we're dividing by the number of total particles because we're taking an average. Now, if we explicitly write out the sum, we see that we have all of these vx squareds. So we have vx1 squared plus vx2 squared, etc., right? Because we're summing up vx, vy, vz for each particle. And all I've done is I've grouped all of the x terms and y terms and z terms together here. And then if we rewrite this as a sum, we see that it's actually the sum over x independently, y independently, and z independently. So we can write these as 3 separate sums. And then, well, because we were dividing each of these sums over the number of particles, we end up with the average of each of them. So at the end of the day, we have our total velocity squared average is equal to the sum of the average of our components of the velocity squared. And in the end, what this ends up letting us do is treat x, y, and z each as having their own energy and therefore contributing their own 1/2 kT to the total energy of the gas, right? So in the end, we're able to say that 1/2 m v average squared equals 3/2 kT, because we got 1, 2, 3 times my 1/2 mv squared.